Hey guys, before you go ahead and do that worksheet today, I do just want to spend a few minutes talking to you about electric pressure in batteries, whether the battery is a source of constant pressure difference, how we're going to sort of change our model of a battery, as well as how we'll begin to change that and how it looks in our circuit diagrams. And then finally, we'll talk a little bit about short circuits and shorting wires and how those affect pressure difference in a battery. This is based on CASL Unit 5, Reading 5, which you do have access to on Canvas in the Files tab. So if you would like to look at that, you may. Okay. Now, first big question, is the battery a source of constant pressure difference? Now, as we've spoken about before, that is the intention of the battery. Its job is to maintain a constant pressure difference, but what we have seen is that the battery is not perfect at doing that. And as we reduce the overall resistance of the circuit, we see that the battery gets worse at doing its job. And so we're going to just take a quick look at why here. Before I really jump into it, I do want to clarify what I'm writing down on this PowerPoint. First, the overall resistance of the circuit, or the equivalent resistance of the circuit, is going to be given by that capital R. But we're going to let the internal resistance of the battery be a lowercase r. So when the resistance of the circuit, the overall resistance, is much, much greater than little r, the internal resistance of the battery, the pressure difference across the battery appears to be pretty constant, as long as the whole resistance of the circuit is a lot bigger than the internal resistance of the battery, which we did decide that the internal resistance of the battery, it's pretty small, but it does get bigger over time, which is what you're going to see in the worksheet. Now, as big R, the resistance of the circuit decreases, the pressure difference lessens. If you remember what we talked about a week ago regarding the principle of series voltage division, when you have different components of a circuit in series, the component that has a greater resistance takes more of the pressure. So as the resistance of the battery and the resistance of the circuit get closer and closer together, the big R, the circuit, starts to take up less of that pressure difference, and the battery itself actually starts to eat its own pressure away, kind of, because its resistance is starting to get big compared to the rest of the circuit. And so when the resistance of the battery is a lot bigger, or even bigger, just a little bit bigger, than the resistance of the circuit, the pressure difference across the battery gets reduced to almost zero. And we're going to look at some pictures here in a second that should help us with that. Now, this is, of course, what happens in a short circuit. The wire has a resistance of zero, but the battery's internal resistance is then not zero, and so it's kind of a lot bigger. And so then when that happens, the pressure difference across the battery would be basically zero then. We're going to modify our battery model, which before just looked like this, and we're going to add a little bit of resistance into our model of the battery. So we're going to say that this symbol here, that represents the chemical activity that's happening within the battery. That is what is trying to move the charge. There's a chemical reaction between the compounds inside the battery that moves charge from the negative side through the battery and towards the positive side. And you might be saying, well, Mr. Dieterle, I thought that charge moved from positive around to negative. And that is true. But if the charge is moving from here around to here, then that means it must be continuing through the battery from negative into positive through the battery. Okay, but it's going around like this. Okay. We're also going to begin to use this symbol in conjunction with this symbol sometimes to reflect the internal resistance of the battery. This is the part of the battery that hinders the movement of charge through the battery. This resistance is due to a buildup of the products of the chemical activity. So there's a chemical reaction happening between two different compounds inside the battery, and it's producing two other compounds which have a resistance. Okay, I want to explain then just how the short circuit works here. Take a look at these three pictures. In the figure on the left, there is no path for the charge to flow from here around to the negative side of the battery. There's no flow path, and so that means that the external resistance, the overall resistance of the circuit, is essentially infinite. Remember, air is an insulator, so it has a resistance that is essentially infinity from here to here. Now, because there is no flow, the internal resistance, R, given by these two little things here, has no effect on the electric pressure difference due to the chemical activity in the battery. Therefore, the pressure difference at the terminals of the battery, here and here, is not diminished, because since there's no flow through here, from here all the way up to here, that's all red, and from here all the way down to here, that's all blue. Okay, so the pressure difference from end to end of the battery is zero. Or I'm sorry, is not zero. It's from red all the way to blue, because the resistance around it is basically infinite and there is no charge flow. In this middle figure right here, there is an external flow path that's present, right? It goes around like this. And in this case, this external resistance, which is from this bulb right here, is greater than the internal resistance, right? It is greater, but it's not much greater. It's not infinitely greater. And so because these are in series, like I was saying earlier, there's that voltage division between each of the circuit elements, this resistance of the battery and this resistance of the bulb. And so some of the pressure difference occurs inside the battery, and then the rest of it occurs outside the battery. Less of that pressure difference occurs inside of the battery, but some of it still does. So therefore, the electrical pressure difference due to the chemical action of the battery is somewhat diminished by the resistance of the battery. And as a result, the electric pressure difference across the terminals of the battery is reduced from orange to green. And this could be this could be a pressure that's very close to red. It doesn't necessarily have to be a whole jump away all the way to orange. It could be like a red-orange or even just close to red, and this could be a blue-green or very close to blue. But as this gets greater, this pressure starts to increase even more from blue up to green and so on and so forth, until the resistance of the circuit over here is essentially zero. So in this figure on the right here, the external flow path consists of only a wire. And remember from Unit 3, we learned that the resistance of a wire is almost zero. It's very, very small. And so when that shorting wire is present, the resistance of the external flow path here reduces until it's almost zero, so that in this case, the internal resistance of the battery, little r, is much greater than the resistance of the external flow path right here, big R. So that internal resistance of the battery is much greater. Since the internal resistance is larger than the external resistance, most of the pressure difference ends up across the internal resistance, just inside the battery. And so as a result, the pressure difference across the terminals of the battery drops to almost zero, and we can color this whole wire, this entire shorting wire, as yellow. Okay, this was a relatively brief discussion about this topic. I do want you to go ahead and pull up Unit 2, Reading 2, and read that again, as well as the worksheet that is published and is due after you watch this. Okay, go ahead and do your best on that worksheet. As always, if you have questions, I'm available in office hours from 2 to 3 p.m. Monday through Friday. Have a good one, guys. Bye.